In today's video, once again we're tackling 6 problems involving graphs. Be sure to watch problem 1 carefully because we will use its solution to help solve some of the later problems. Let's start with a quick recap. A graph is a set of points, called vertices, connected by lines, which we call edges. Each edge connects exactly two vertices. The degree of a vertex is the number of edges connected to it. In problem 1, we need to show that the sum of the degrees of all vertices in a graph is always equal twice the number of edges. First, let's test it with an example. Here's a random graph. If we add up all the vertex degrees, we get 22. The graph has 11 edges and 11 times 2 is 22. So, the statement seems true. Now, let's actually prove it. Imagine highlighting both ends of every edge. The degree of a vertex is the number of highlights it has. Thus, the total sum of degrees is the total number of highlights. Since each edge contributes 2 highlights, the total is exactly twice the number of edges. And that's our proof. In problem 2, let's prove that the number of vertices with odd degrees in any graph is always even. Let's use a proof by contradiction. Suppose a graph has an odd number of vertices with odd degrees. From problem 1, we know that the sum of all degrees equals twice the number of edges, so it must be even. However, if there is an odd number of odd degree vertices, their sum is odd. Adding this to the sum of an even degree vertices, which is even, gives an odd total. This contradicts the even total we proved earlier. Thus, the number of odd degree vertices must always be even. In problem 3, is it possible for 9 line segments to intersect exactly 3 others each? Instead of trying to draw such a diagram, let's analyze it mathematically. Represent each segment as a vertex in a graph and connect vertices if the corresponding segments intersect. Now, there are 9 vertices, each with a degree of 3. The total degree is 9 times 3, which is 27. But using the formula from problem 1, the total degree must be twice the number of edges. Since 27 is odd and cannot be divided by 2, we have a contradiction. So, this arrangement is impossible. In problem 4, can it happen that 9 students each have 3 friends, 11 students each have 4 friends, and 10 students each have 5 friends within a class of 30. Viewing the students as vertices in a graph, their number of friends corresponds to the degree of each vertex. Adding up the degrees, we get 27 plus 44 plus 50, which is 122. But from problem 1, the sum of degrees must be even. Since 121 is odd, such situation is impossible. In problem 5, 7 islands are connected by either 1, 3 or 5 bridges. Must at least one of these bridges connect to the shore. Let's assume the opposite, that all bridges connect only between the islands. Here, the islands are vertices and the bridges are edges. Each vertex has a degree of 1, 3 or 5, all odd numbers. Adding these odd degrees for 7 vertices gives an odd total. But as we know, the sum of all degrees in a graph must be even. This contradiction proves that at least one bridge must connect to the shore. In problem 6, prove that a connected graph where every vertex has an even degree remains connected after removing any single edge. Suppose this isn't true and removing an edge splits the graph into 2 disconnected parts. Removing the edge decreases the degree of 2 vertices by 1 in each part, making them odd. Now, in one part, all other vertices still have even degrees. Adding these along with the single odd degree results in an odd sum. But as we know, the total degree in any graph must be even. This contradiction shows that the graph remains connected even after removing an edge. That's all for today's video. If you have further questions, leave them in the comments. See you in the next one. Bye.